So for part 2 of chapter 27, we're going to be looking at more about this intuition that we should have about regression, because we've done all of our assumptions and conditions checking, and then we say that we're going to hit the calculator button. And I want you to think, like, wait a minute, we're just moving forward and using the computer to do these calculations, but we haven't discussed anything about standard errors for slope or y-intercept. And so if our sample is representative, it will produce a model with a slope, so our sample will produce a slope of b1, whose expected value is the true slope, so we use beta 1 to talk about that true slope. Different samples will produce different models with different slopes, and that should make sense. But we want to look at what aspects of the data affect how much models, i.e. slope and intercept, vary from sample to sample, and that's where standard error comes into play. And it's not as simple when we're talking about standard error in this case, because we have a lot of different factors going on. So what affects the standard error for our slope and for our y-intercept? Do we have any indicator that might suggest the variability between regression models from different samples? So we have three things that we are going to look at here. The first thing is we want to look at the spread around the line. And if you remember, this spread is called the standard error of the residuals. So what we're looking for is in the first part. The less scatter around the line means the slope will be more consistent from sample to sample. The more scattered our points are around our least square regression line, the less consistent it will be from sample to sample. There will be more variability. And the less scatter around the line means the slope will be more consistent. The spread around the line is measured with the residual standard deviation, or S sub e. You can always find S sub e in the regression output, and it's usually labeled S. And this is a little confusing piece because there's no subscript. So if you see S, it's the same thing as S sub e, or the residual standard deviation. So next thing that we want to look at is not just the spread around the line, but the spread of the x values. So how far things are horizontally. And in general, a large standard deviation of x, which we call S sub x, provides a more stable regression. We want more spread horizontally, and that gives us a large range of x values, makes more consistent models similar to points far away, create more accurate lines. So we want the x values to be spread across because it makes our line of best fit more consistent. And the last thing, which is pretty obvious, is if we have a larger sample size, it will give us more consistent estimates. And we're talking about more consistent estimates or lower variability. We're saying that the standard error measurement, when we use it for hypothesis testing, or when we use it for confidence intervals, is small. And that's what we want. So how do you calculate the standard error for your slope? So using these three aspects, the standard error of the residuals, the standard deviation for our x values, and our sample size, we get this formula for the standard error. So we have standard error for our slope is equal to standard error or standard deviation of our residuals divided by standard deviation of the x values times the square root of n minus 1. And I want you to make a note of this formula because we're going to see this again and again. It's not necessarily written on the formula sheet from the AP test, but it's good to have on hand. So when we put those together, and this should also look familiar to you guys, when the conditions are met, the standardized estimated regression slope follows the student's t-model, this time with n minus 2. And if you want to know why it's n minus 2, just like we had before, when we learned about regression before and we didn't know everything, so we said, we don't know what the true mean is, so we're going to say n minus 1. This we have much more going on, so we say degrees of freedom is n minus 2. So t sub n minus 2 would be our observed slope, so our observed minus our predicted or our model divided by our standard error. And this formula is the same from situation to situation to situation. It's just what values that we plug in that are different. So we estimate the standard error with our standard area for a slope formula. Now, this is where, if you remember way back, to calculate standard error, it's the sum of the differences of the y's squared divided by n minus 2. And this gives us our standard error for our residuals. N is our number of data values, and standard deviation of x, or S sub x, is the ordinary standard deviation of the x values, which we are going to be given in most of these outputs. Now, what the AP formula gives you is this mess of a formula. And what you need to realize is that this S sub B1, or the standard error for our slope, is just our standard error for our residuals. That's our numerator. And then we have our standard deviation for our x values, which goes up here. So if we put those two formulas together and do a little bit of simplifying, we get our nice and easy formula. Now, oftentimes you're going to be given a computer output that has all of these values in there. And you're going to have to figure out what value goes in the numerator and what goes in the denominator. And just to go back to this formula, we were saying we want small amounts of scatter, or the points, to be around our line. This makes the numerator small, which makes our error small. We also want the standard deviation for our x values to be large, which makes our denominator larger. And we also want more points. So if we have more points, it makes our denominator larger. If all of these factors, or any one of these, fits, that decreases our standard error, making our measurements more consistent and our predictions more accurate. Now, you might be saying, okay, that's a lot about slope, but what about the y-intercept? So the same reasoning applies for the intercept, and we can write students t equals our y-intercept value that we found minus our predicted all over its standard error, but we rarely use this fact for anything, just to be honest with you. The intercept often is not interesting, and most hypothesis tests and confidence intervals for regression are about the slope, and that's what we care about. So yes, you can do this for y-intercepts, but in general, we're going to leave that be. So then we get to our hypothesis testing. So a null hypothesis of a zero slope suggests that the entire claim of a linear relationship between two variables is not valid. That is the whole point of any hypothesis. Is there a relationship, or is what we observed simply due to chance? And if you think about with a scatter plot, if there's no relationship, then there's no line that we can draw. So the best line that can fit this model has a slope of 0. So when we do a hypothesis, we hypothesize, or our null hypothesis is that the slope is 0, aka there is no relationship. And we find our t-statistic using our model, or our predicted slope, minus 0 over our standard error for our slope. And we continue as we would with any other t-test. With a confidence interval, the formula for a confidence interval for a slope is as follows. We have our slope that we found from our regression model, plus or minus our t-statistic with n minus 2 degrees of freedom, times our standard error for our slope. I need you to write this formula out. Get in the habit, if you're giving a confidence interval, at the very least, write this out before you give me what the calculator is telling you. It's critical to showing your work and showing that you understand what you're doing. So once we have a regression model, we will be tempted to attribute too much validity to this model. Remember, the model is most likely wrong for any individual prediction. Not all of our points are going to fall on that line, which is why we say it's likely wrong. So as we've done with other statistics, we have standard errors, and we can use those to construct confidence intervals for the predictions. Specifically, finding an interval within which we believe the true slope will fall. Remember, all models are actually wrong. That does not prevent those models from being useful, though. Just do not be too enamored with what you found. So if we are going to use standard errors for predicting values, think back to our example with percent body fat and waist size. There are two questions that we could ask and that you will be asked. Do we want to know the mean percent body fat for all men with waist size of, let's say, 38 inches? And the other way to think about it is, or the other question we could ask is, do we want to estimate the percent body fat for a particular man with a 38-inch waist? And so the predicted percent body fat is the same in both questions, but we can predict the mean percent body fat for all those men with waist size 38 inches with a lot more precision than we can predict the percent body fat of a particular individual. So the mean, more precise. And this, for a particular individual, we will see that it's a wider range. So remember the distribution of that 38-inch that I showed you when we moved into this. That's what we're examining. And you might be seeing a symbol that we haven't seen in a little bit. I think this was introduced in chapter 23, but that x sub nu, remember that is that Greek letter nu, is another way of writing degrees of freedom. So all we do is say x sub nu is our 38 inches, is the degree of freedom that we're looking at to predict either the mean or the actual value at x. So we start with the same predictions in both cases. So we are predicting for a new individual, one that was not in the original data set. And the regression model predicts the percent body fat as, well, here is our regression formula. We have our y-intercept, and we have our slope. So y equals a plus bx, or b naught plus b1x. And we have our confidence interval for both predictions will take the form of y hat of 38 plus or minus our t critical value of n minus 2 times our standard error. Here is the only catch. The standard errors will be different for the two questions. And these will just be two new formulas that we're going to throw into the mix. So the standard error for the mean predicted value will be our standard error squared times x sub nu minus the average x squared plus our s, or s sub e, squared over n. Fun formula. And additionally, which makes our range wider, individuals vary more than means, so the standard error for a single predicted value is larger, which is factored in with this additional standard error of the residuals. If you want to see where these formulas come from, I highly suggest you read the book. But if you don't plan on reading it, just take it at face value. These are the two formulas for standard error for these two specific questions that you will need. So keep in mind the distinction between the two kinds of confidence intervals. The narrower interval is a confidence interval for the predicted mean value at x sub 38 in this case, or x sub nu. While as if we're trying to make a prediction interval for an individual with that x value, it's going to be a wider interval. So the narrower interval is for the mean, the wider interval is for the individual. And this is what it looks like. So if you take a look at the difference between the predicted value, predicting for mean and predicting for the individual, the green band is for the predicting for the mean versus the red band, this dashed line on the outside, that is our prediction for our individual. The solid green line near the regression line shows the 95% confidence interval for the mean predicted value, and the dashed red line shows the prediction intervals for individuals. So save those formulas for later. Let's wrap up this section by covering some words of caution. We'll have one more video that goes through a handful of examples and is going to pull back that math and anxiety data that we did for reviewing regression. So some words of caution. Remember, do not extrapolate beyond your data. It's always dangerous to predict X values that lie far from the center of the data. We need to watch out for highly influential points. We need to watch out for outliers. Also watch out for one-tailed tests. So tests of hypothesis about regression coefficients are usually two-tailed. So software packages and the calculator often just spits out reports for p-values for two-tailed tests. If you are going to conduct a one-tailed test and you know specifically it goes one way, you'll need to divide the reported p-value in half. So just a word of caution. So we're going to end it there. We're going to finish up this last video with our 2 example problems, and then we are done with all new material from AP Stats. Take care, Falcons.